Hello and welcome to the CTech webinar. At this point, I'd like to hand things over to Bruce Vigon, the Scientific Affairs Manager for CTech. Bruce, the floor is all yours.
Thanks, Colin, and welcome everybody to today's webinar. CTech is really pleased to be able to bring this event to you, and as this is our first one, we are actually very much interested in getting your feedback. There will be a survey available to you at the end of the webinar, and in fact, the way it's set up, you are allowed to have multiple folks at your listening and viewing location if they want to provide individualized comments. We would welcome that. So without further ado, let me get into today's webinar and introduce our first speaker. Our first presenter is Dr. Gary Kleschka. He's a senior fellow with the Toxicology and Environmental Research Lab at the Dow Chemical Company. And his area of focus in this broad topic of POPs and PBTs is evaluating the persistence and transport potentials of PBTs, and in particular understanding the fate, transport, and biological effects of those compounds. Gary, the floor is yours.
Thank you, Bruce. I, too, would like to welcome everybody to today's webinar on science-based guidance for the evaluation and identification of PBTs and POPs. Together with our other presenters, Derek Muir and Michael McLaughlin, we're going to be presenting an overview of the findings of a recent CTech Pelston workshop. Let's begin with some definitions and a historical perspective. First, what are POPs? Persistent organic pollutants are bioaccumulative and toxic organic compounds of natural or anthropogenic origin that resist photolytic, chemical, and biological degradation. They're characterized by low water solubility and high lipid solubility, which results in bioaccumulation in the fatty tissues of living organisms. POPs may be transported in the environment at low concentrations by movement of fresh and marine waters, but recent evidence has shown that because of their semi-volatility, POPs are also transported long distances in the atmosphere, resulting in widespread distribution around the Earth, including regions where they have never been produced or used. So both humans and ecosystems may be exposed, and in many cases for extended periods of time. So simply stated, POPs are organic substances which meet persistence, long-range transport, bioaccumulation, and toxicity criteria, and are distinguished from the broader class of PBTs because that class may also include metals. Beginning in the early 1990s, regulatory authorities around the world have been interested in PBTs and POPs. And since that time, there's been a progression of regulations, both at the national and international levels, which identify various PBT substances and require action to control the use and or release of these substances. These include a number of historical initiatives, many of which are still in force. Those include the Oslo and Paris Commission's Convention for Protection of the North Atlantic, which agreed that discharges and emissions of substances that are PBT and could reach the marine environment should, regardless of their source, be reduced to levels that are not harmful with the aim of their elimination. The Fourth International Conference on Protection of the North Sea in 1995 set a goal to eliminate within one generation releases of PBTs to achieve environmental concentrations that approach background levels. Similar actions were taken in the Barcelona Convention for the Protection of the North Sea in 1995, Mediterranean Sea, and then in 1997 an amendment to the Canadian and U.S. Great Lakes Water Quality Agreement agreed to emphasize action on PBTs and POPs in the Great Lakes Basin. More recent regulations include the 1999 amendments to the Canadian Environmental Protection Act, requiring categorization and screening of all substances on Canada's domestic substance list. In the United States, there are several regulations which specifically address the evaluation of PBT substances, including the Toxic Substances Control Act, and the Toxic Release Inventory under the Emergency Planning and Community Right to Know Act. In the European Union, we have several regulations, both the previous existing chemicals legislation as well as the current Registration, Evaluation, Authorization of Chemicals, or the REACH program. Both of these required the assessment of PBT characteristics. And then finally, we have several international treaties that have also been approved, beginning with the 1998 United Nations Economic Commission for Europe, a Convention for Long-Range Transboundary Air Pollution, And then finally in 2001, the United Nations Environment Program, the Stockholm Convention, a legally binding convention with measures to reduce or eliminate 12 specific persistent organic pollutants that were named in the treaty, but the treaty also included criteria and procedures for selecting candidate substances for further international action. The criteria for evaluating persistence, bioaccumulation, and toxicity characteristics of substances under the various regulations are not harmonized, but they do show large similarities. And this slide is intended to provide an overview of the PBT criteria for a number of national and international regulations. And as we'll discuss in the next section, persistence is assessed with respect to environmental half-lives in various environment compartments, including water, sediment, soil, and air. And it's important to note that the atmospheric half-life often provides an indication of the potential for long-range transport potential of that chemical in air. Bioaccumulation potential is assessed using either octanol water partition coefficients or values for the bioconcentration or bioaccumulation factors. And then criteria for assessing toxicity vary considerably among the various regulations and often require the use of expert judgment. And many of these regulations assess both mammalian and environmental toxicity. In addition to differences in criteria, the various regulations can also be divided based on their objectives. In other words, what are they trying to accomplish? Many countries have regulations requiring that any new substance notifications or chemical registrations be evaluated with respect to their PBT characteristics. New substance regulations of this type are common in the U.S., Canada, and Europe, and they are becoming common in the emerging geographies. And then in Europe, certainly REACH will require PBT assessment of all substances which are registered over the next 8 years. Governments have also enacted regulations which require screening of all substances on their chemical inventories. For example, the 1999 amendment to the Canadian Environmental Protection Act required that Environment Canada and Health Canada categorize all 23,000 substances on the domestic substance list with respect to their PBT characteristics. And similarly, the European Chemicals Bureau has also conducted an assessment of all of the high production volume substances on their inventory. And then finally, criteria and procedures for the nomination and evaluation of PBTs and POPs are also described in the UNECE-LRTAP and UNEP conventions, and each of these treaties provide for the addition of new substances. So from this background, it should be apparent that POPs and PBTs will continue to be the focus of regulatory attention. Because of its global nature, the Stockholm Convention was used as a foundation for much of the discussion at the CTech workshop. As previously noted, the Stockholm Convention is a global treaty under the United Nations Environment Program. It was adopted in 2001 and entered into force in 2004. To this point, over 152 parties have ratified the convention. The U.S. has signed the treaty but has not ratified because of conflicts with existing regulations. The conventions establish a global regime for phase-out of or restriction of various POPs, including chemicals, pesticides, and certain byproducts. In addition, as I said, to listing 12 specific POPs in the treaty, language is provided for the nomination, evaluation, and addition of new substances. And guidance in the treaty refers to several distinct activities. Screening is where a review committee conducts an initial review of the properties of the substance compared with the criteria. The substance passes a risk profile is then prepared for that substance, which is then evaluated also by the review committee. And documents at this point allow the committee to evaluate whether the substance is likely, as the result of long-range transport, to lead to significant adverse effects such that global action is warranted. The precautionary principle is embraced by the Convention in that the lack of full scientific certainty should not block further action. And then finally, the treaty also provides guidance for a risk management evaluation, which includes the evaluation of possible control measures, socioeconomic impacts, as well as the efficacy of alternatives. So summarized in the previous slides, the current regulations define candidate PBTs and POPs in terms of fairly strict criteria that are based on the state of the science in the early 1970s and early 1980s. And since then, an evolution in environmental and analytical chemistry, computational chemistry, information technology, as well as toxicology has produced new insights into persistence, bioaccumulation, and toxicity of chemical substances, and we have a variety of new methods to identify these chemicals. Unfortunately, regulatory criteria has not kept up with the rapid development in the science, and as a result, scientists in governments, industry, and academia find themselves in a situation where the guidance is sometimes available but may be limited and sometimes out of date. So what was CTech's response? To foster development of a sound scientific foundation for the evaluation of PBTs and POPs, CTech has sponsored 2 Pelston workshops. In 1997, a workshop was held which focused on the evaluation of persistence and long-range transport potential only. And then in 2008, a workshop was held to develop guidance on the assessment of all of the characteristics, including persistence, bioaccumulation, toxicity, long-range transport, and the potential to cause significant adverse effects. These workshops had broad representation from academia, government, and industry, as well as from the geographies, and the approach at these meetings has been to discuss the science, reach consensus, and make recommendations. CTech has used various means of communication to convey the findings of the workshop. There are a series of publications. The first workshop was published in a book, while the results of the second workshop were published in a series of articles in the journal Integrated Environmental Assessment and Management. We've also made numerous publications and presentations at CTech meetings, both in Sydney, Warsaw, and in Tampa, as well as Derek made a presentation to the UNEP Stockholm POPs Review Committee. CTech is also sponsoring a series of webinars, and today's session is intended to provide you with an overview of the findings of the workshop, but other webinars are planned to cover specific topics in greater detail. And as Bruce mentioned, at the end of this webinar, we will be seeking your input on specific guidance that you're most interested in learning more about. So the remaining topics for discussion will focus on recent advances in the evaluation of environmental persistence, overall persistence, multimedia partitioning, and long-range transport potential. And then I'll turn it over to Derek, who's going to speak to bioaccumulation potential and ecotoxicity and the significant adverse effects aspects of the treaty. And then Michael will finally cover the exposure to wildlife and humans and a framework for assessing the likeliness for significant adverse effects. So let's begin with a session on environmental persistence. The persistence of organic compounds is governed by the rates at which they are removed by chemical and biological processes, including biodegradation, hydrolysis, atmospheric oxidation, and photolysis. And this slide is intended to illustrate the complex processes in the environmental compartments which are important for assessing persistence. At the workshop, this work group focused on evaluating persistence of compounds in all of the environmental media, air, water, soil, and sediment, in terms of their single medium degradation half-lives. And these findings built on the results of the previous 1997 workshop, as well as guidance that had been developed for other chemicals assessment and regulation programs. The primary aim of the work group was to provide guidance to authors and reviewers of chemical dossiers in both the government and private sectors. And the second objective was to provide a summary of the current state of the science with respect to the assessment of POPs. As I mentioned earlier, most frameworks designed for assessing persistence use degradation half-life thresholds to determine whether a substance should be considered persistent. And this figure illustrates the effect of half-life on the environmental accumulation of 4 hypothetical substances. For the purposes of the illustration, each of the substances is assumed to be emitted at the same constant rate for 100 days, at which point the emissions cease. So it's evident that substances with very short half-lives in the 1 to 10 days show only modest accumulation in the environment and are quickly eliminated when the emissions stop. In contrast, substances that have longer half-lives remain in the environment to potentially exert toxic effects, bioaccumulate, or be transported to regions far from where they're manufactured or used. It's important to note that physical processes like dilution and advection, which do not affect persistence in the environment because they do not reduce the environmental burden. Unfortunately, the decision process in designating a chemical as persistent is not straightforward. Persistence is often inferred from the continued presence of a substance in the environment distant from the sources of emission, or from the slow rate of degradation and laboratory screening or simulation tests. A common misperception is that environmental persistence is an inherent property of the substance and that we can easily measure it. For example, we can easily measure properties, the physical and chemical properties of a substance. But for most degradation processes, this is not the case. Rates of degradation of a substance are determined by a combination of both substance-specific characteristics as well as the environmental conditions. Chemical structure ultimately determines which transformation processes may be significant for a given compound and which are not likely to be important. Structure also determines inherent properties such as water solubility, vapor pressure, and those can also influence degradation rates or the relevance of an environmental compartment. Characteristics of the receiving compartment are also important. In air, the hydroxyl radical concentration is important, as well as for surface environments, temperature, salinity, pH, oxygen levels, redox status, the test chemical concentration, and nutrients are also important because these may directly or indirectly impact the rates of transformation of a chemical in the various media. When evaluating environmental persistence, a tiered approach is recommended, and in this case, the chemical is first examined at the screening level. For example, we might test for ready biodegradability or hydrolysis. And then this is then followed by a more detailed examination in the confirmatory phase. The assessment of the chemical should also involve a careful analysis of all relevant data and a comparison of the relative merits of the studies to determine persistence based on a weight of evidence set of evaluation. In principle, results from higher tier studies, for example, the simulation tests, have greater environmental relevance, and therefore these should carry more weight. Among the findings and recommendations of the persistence work group, when evaluating persistence, expert judgment is often needed to develop the weight of evidence. And this may include the use of standard and non-standard data, including structure-activity relationships, or QSARs. However, preference should be given to valid experimental data over non-test data such as QSAR predictions. No single half-life can adequately describe the degradation in the environment for any environmental compartment. And oftentimes in the literature, a range of half-lives is reported. The work group concluded that it's not appropriate to use the slowest or most conservative half-life. Instead, the work group recommended that using a half-life in the higher end of the observed range or a measure such as the geometric mean. And then finally, it's generally accepted to combine process rate constants for an environmental compartment by summing first-order rate constants for that compartment. For example, a chemical may be degraded by both hydrolysis and biodegradation in water, and it's appropriate to sum the half-lives for both of those processes for comparison with persistence criteria. The work group also recommended that substances that degrade in the screening tests can be considered non-persistent. And for example, a ready biodegradability test would be considered a screening test. However, it may be necessary to demonstrate that no persistent degradation products are formed, and if stable degradation products are formed, it is appropriate to evaluate persistence of the parent substance based on an assessment of its degradation products. Very important topic that was discussed is whether or not rate constants should be adjusted for environmental conditions. That may be appropriate for very refined assessments, but given the uncertainties, the simplest approach recommended by the work group is to avoid such practices. For example, it's not sound science to use the Arrhenius equation or the Q10 rule to adjust biodegradation rate constants to representative environmental temperatures. This is because different microorganisms have different temperature optima, and the microbial populations are generally adapted to the prevailing environmental conditions. And the result is that the transformations that the microorganisms perform cannot be reliably scaled for temperature. Another important topic is physical removal by sorption or the formation of bound residues. Oftentimes in sediment studies, the formation of non-extractable residues are formed, which cannot be recovered by exhaustive extraction from the solid matrices. It's important when the formation of non-extractable residues or bound residues is observed, the results need to be reported in a transparent way. The workshop concluded that when non-extractable residues can be shown to be covalently bound to the soil or sediment material, that the rates of dissipation, which include this bound residue formation, can be included with the degradation rate constants for comparison with persistence criteria. So what I've done is given you a very high-level overview of the results of the persistence workshop work group. And for more information, I'd refer you to the article by Bob Bothling, published in IEAM. I'd also like to acknowledge the work group members that participated at the workshop. An important feature of chemicals released to the environment is that they can redistribute themselves between media. For example, a substance may be released to the air, water, or soil, and then subsequently move between these phases. So it's important to assess the ability of the compound to undergo multimedia partitioning, because this behavior will affect the compound's susceptibility to degradation in a particular compartment, as well as ability to be transported in air or water over long distances. The distribution of chemicals in the environment is controlled by physical chemical properties and by certain features of the environment. And evaluative models have been developed to make predictions about chemical distribution in multimedia systems, and such models are important tools for profiling behavior. A number of phys-chem properties are very important for determining how a chemical behaves, such as water solubility, vapor pressure, the partition coefficients, etc. And different estimation methods may be used to derive these physical chemical properties. But it's important to note that phys-chem property reported in the literature are often inconsistent or incomplete, and that's because the quality of the data determines the reliability of any POPs or PBT assessment. So it's important to review such data carefully, and the partition properties need to be checked for internal consistency to ensure outliers are identified and removed from the data set. Environmental behavior is further developed by combining the assessments of the multimedia distribution of the chemical with information on its degradation kinetics in different media. As I previously discussed, environmental half-lives can be determined by a variety of experimental methods, and when half-lives are not available from experimental results, you can use QSAR information to estimate environmental half-lives. In the current regulations, persistence is often assessed by comparing criteria for single media half-lives, typically for relevant environmental compartments. That is, the compartments in which the compound is likely to reside. However, such approaches often overlook the redistribution of chemicals in multimedia environment, so this work group recommends that further assessment with respect to overall persistence be evaluated in the global environment. There are several multimedia models that have been developed to evaluate the overall persistence of chemicals. The OECD, Organization for Economic Cooperation and Development, supported the development of an inter-laboratory comparison of one approach that led to the development of the OECD POV and long-range transport potential tool, which allows comparison of the properties of a test chemical against a series of reference compounds. So it's possible to define a POV value, or overall persistence value, that ensures no net accumulation of a chemical in the environment. But because the overall persistence depends on environmental conditions, it's inappropriate to define specific POV cutoff criteria. Rather, this information should be used as a part of the weight of evidence for screening and evaluating chemicals. Atmospheric transport is usually the primary mode for conveying substances to remote regions, and for this region, the UNEP and UNECE conventions define criteria for half-life in air, of greater than 2 days. The original intent of this value was to highlight those chemicals that are sufficiently persistent to be able to transport through the atmosphere to remote regions, and 2 days is a convenient metric that may apply to substances that are emitted in parts of the temperate world, which may travel with some efficiency to the Arctic. And the OECD Long-Range Transport Potential Tool permits an assessment of this potential for candidate substances, and those results can be compared with the properties of well-known compounds. This work group also addressed the role of monitoring data, and regulatory approaches often acknowledge the usefulness of monitoring data, often monitoring data from remote locations, for highlighting potentially problematic substances. This occurrence in remote regions is often taken as evidence of their persistence and long-range transport potential. However, the work group feels that detection of a chemical in the remote area is not evidence per se of these properties, and that a more careful evaluation of environmental concentrations as well as temporal and spatial trends in the field are required. Detection in remote environments must be assessed according to the amounts and patterns of uses and emissions and the sensitivity of the analytical methods if a robust and scientifically sound profile is to be developed. So again, I've tried to give you quickly a high-level overview of the findings of the long-range transport potential work group. For further information, I'd refer you to the publication by Martin Scherriger and co-workers, and this slide also acknowledges the other work group members that participated to this session. So with that, we're going to conclude part one of this topic, and I believe we may have time to entertain a few questions. Bruce?
Thank you, Gary. Appreciate that overview. We actually have one comment from our audience, and I will quickly go through that, and that is that the number of signatory parties to the Stockholm Convention now is up to 170, and this is an indication that organizations, countries continue to sign on to the convention so that the breadth and reach of it continues to increase over time. I think given our time, we'll move along to the second segment of our presentation for you today, and I'll introduce our second speaker. He is Dr. Derek Muir of Environment Canada. Dr. Muir leads research on the long-range transport and fate areas, and his expertise in this topic derives from several decades of experience measuring POPs as well as fish and wildlife exposure to these compounds. Derek?
Thanks, Bruce. This section of the webinar deals with bioaccumulation, and then I'm going to turn to ecotoxicity, so two somewhat different topics, which I'll try to cram into about 30 minutes. In the bioaccumulation section, I will define various measures of B and provide a brief overview of in vitro and in silico approaches to predicting bioaccumulation, because I think these have been the most exciting areas where there's been new developments in the past 10 years. And then we'll also look at measurements of B in field studies, including the use of the trophic magnification factor, concluding with some recommendations for bioaccumulation assessments. So why study B? The process of chemical bioaccumulation is vital to understanding whether a substance accumulates or biomagnifies sufficiently to cause significant adverse effects, either in individual organisms or in populations, and ultimately to ecosystem structure and function. Bioaccumulation is generally referred to as a process in which the chemical concentration in the organism achieves a level that exceeds that in the respiratory medium, water for fish, air for mammals, and of course from the diet or both. The extent to which chemicals bioaccumulate is expressed by various parameters, which I'm sure most attendees on this webinar have heard about, such as BCF and DAF, and I'll define these so we're all on the same page on that in the next few slides. The graphic here is just meant to illustrate some of the various pathways of accumulation and loss, and we'll come back to some of these pathways in a future slide. The bioconcentration is used to describe the steady-state concentration of a chemical in the organism from water uptake alone. And so you just simply have the equation of concentration divided by water at a steady state. The BCF is a very widely used parameter. However, in the context of POPs and PBTs, it is not regarded as a good descriptor of biomagnification capacity of chemical substances. BCFs are difficult actually to determine with poorly water-soluble organic chemicals, such as many chemicals that are classified as POPs, and they're time-consuming to do, costly, and they use vertebrate animals. Bioaccumulation is essentially the same equation. However, it refers to the exposure from all sources, from diet and water, and therefore it really applies mainly to field studies, while BCF is restricted to lab studies where the water is the only route of uptake. Note that the water concentration is also important here, and it should reflect the dissolved phase. So there's some challenges sometimes in measuring that water concentration. Turning to biomagnification, it generally refers to the accumulation in higher trophic levels of the food web, where exposure to the chemicals takes place mostly through food consumption rather than water uptake. Now, the use of the BMF assumes the predator is in a steady state with its environment and that there's one trophic level between the predator and the prey. Usually BMFs are lipid normalized because percent lipid can differ between predator and prey, and also because the organics are associated with lipid. This isn't always true in the case of chemicals like PFAS and methylmercury. Because BMFs can vary with diet, they need to be adjusted, or they can be adjusted via a trophic level adjustment. This was published by Fisk et al. In an ES&T paper. And it should be noted that BMFs can also be determined in the lab from dietary feeding studies, and we'll mention that a bit more in another slide. The drivers of interest in bioaccumulation come from the Stockholm Convention and various legislation and regulations that Gary mentioned in his part of the presentation. And I've reintroduced a segment of the table he showed just to discuss the BCF and BAF criteria. So under the Stockholm Convention, if the values of BCF or BAF on a wet weight basis are greater than 5,000, or the log KOW is greater than 5, this is evidence of bioaccumulation. Also, the Stockholm Convention allows for other evidence, such as monitoring data, which is sufficient to justify the consideration of the chemical. And also under other existing programs, such as REACH and the TSCA in the U.S. and so on, the slightly different criteria are used as shown here, but it's typically 2,000 or 5,000. Now I'd like to turn to the use of in silico models and also in vitro approaches, because I think, as I said, this is a more exciting area of new developments. It was discovered early on that when you plotted BCFs against log KOWs, you got a curvilinear or linear relationship depending on the values of the log KOW, and you can see that on the left-hand side figure there, representing various work starting in the late 70s and early 80s. Essentially, all the data were fitted with a best fit techniques, and the QSAR models early on tended to lump all compounds into one fitted equation. More recent models have taken specific chemical properties into account, such as ionization potential, and are more empirical in a sense of for example, in BCF Win, which is a free program available as part of the EpiSuite software package, ionizable substances are assigned a default log BCF equal to 0.5 if they have log KOW less than 0, and also substances with very high KOWs are assigned 0.5. And the other aspect of that right-hand graphic that's worth thinking about is the number of data points. There's approximately 690 substances there, but this represents, of course, only a small fraction of all the chemicals in commerce, and is a concern from the point of view of fully predicting all the various chemistries out there. BCF Win makes use of molecular structure and has recently been modified to include metabolic transformation rates, which is a major advance in the application of that model. Now I'd like to look at a bioaccumulation model. This incorporates a mass balance concept in which you have all routes of uptake and loss, or essentially an ADME process or combination of processes. The equation includes partitioning to non-lipid portions of the organism, the uptake from the water and diet, elimination, as well as growth dilution. Diet and food web part, you have the various Greek letter terms there of empirical beta, an empirical overall biomagnification factor, tau, a degree of trophic dilution, and phi, a biomagnification factor, or a fraction of bioavailable, sorry. Several of these equations can be put together to create a food web model as well. All the models like this explicitly or implicitly incorporate knowledge of ADME processes. Now, the information on this is typically available for things like PCB congeners, but it can be really lacking for many other substances in commerce that are maybe, for example, high production volume chemicals. And of all the ADME processes and the processes shown here, metabolism is long recognized as an important source of uncertainty in the BCF-BAF predictions. So this is a challenge then to determine these parameters with unstudied chemicals. So if we take that equation and essentially rearrange it, we can estimate the BCF. Essentially, it represents the uptake rate from water divided by the elimination over the gills, K2, and as well as a growth and a metabolism term. These are all first-order rate constants with units of hours or days to the -1. The BMF represents essentially the same approach, but it would be the dietary uptake divided by the various elimination pathways. Now, for the BCF, there's an accepted protocol, the OECD 305 Standard Bioconcentration Test. However, standardized protocols for determining lab-based BMFs do not currently exist. There is an OECD working group focusing on this, and an inter-lab study is planned, actually. But there's been a lot of work in terms of applying dietary bioaccumulation studies to measure BMF in fish and mammalian species, in which the administered food is spiked or naturally contaminated and then fed over a period of time to the test animal. If we then look at this equation again, to be useful for screening a wide range of chemicals and also to avoid costly bioaccumulation studies, the various parameters circled here need to be able to be estimated from in vitro methods. And there's been much work on this in the past 10 years. On the partitioning side in blue, this has been related to estimating uptake with human intestinal epithelial CACO2 cell lines, and also with parallel artificial membrane permeability assays, or PAMPA. These systems are borrowed from the drug bioavailability and drug discovery area, but they've generally been applied only to relatively hydrophilic chemicals, but recently a modified PAMPA has been shown to be predictive of passive elimination of non-metabolizable hydrophobic chemicals. On the elimination and metabolism side, in green, the use of microsomal or S9 liver fraction of fish hepatocytes or liver slices has been used, and the results scaled up to whole fish, which is an important development. So putting all of these terms together in terms of in silico and in vitro, you have I've combined them all in this slide, and we can envision a future scenario where BAFs and BMFs can be estimated accurately by extrapolating in vitro results to in vivo scale and reparameterizing the model. And the working group chaired by John Nichols of EPA concluded that we are at the proof of concept stage for the extrapolation of microsomal or liver fractions in vitro metabolism to in vivo. To summarize a little bit on the in vitro and in silico approaches, the in silico approach for prioritization and assessment of potentially bioaccumulate chemicals is an essential tool, given the lack of data for many substances that are existing substances in commerce, for example. In vitro test systems are emerging as essential tools for estimating metabolism and membrane transfer, and they offer many advantages for predicting ADME properties when compared to whole animal testing. But metabolism remains a major uncertainty, although there's promising results in terms of extrapolating these in vitro systems with like microsomal fractions, to in vivo. The mechanistic nature of more recent models, such as what I described in the previous slide, makes them more transparent and the ability then to incorporate in vitro derived ADME information. And there's also progress being made towards structure-based estimation of metabolic rate constants. But one cautionary note needs to be added, and that is that the domain of applicability or boundary conditions of the results generated from both in silico and in vitro approaches needs to be understood so they're appropriately applied. Moving on to field measurements, data derived from field studies of bioaccumulation are the ultimate indicator of whether a chemical's B potential is actually expressed in nature. Studies using organisms collected in the field integrate multiple exposure routes and processes that may both enhance or attenuate measures of B, and ultimately with the goal to identify substances that are subject to trophic level transfer and biomagnification due to concern over their long-term chronic exposure, and particularly for top predators in humans. That's really the goal and the underlying the assumption of this field work. So trophic magnification factor is an example of how to organize and interpret the data from field studies. It represents the average prey to predator transfer of POPs through food webs. It's calculated from the slope of the log transform concentrations of POPs, usually lipid-adjusted concentrations, versus trophic level. It eliminates the need for BMS calculated with individual predator-prey species, which can be highly variable from one predator-prey combination to the other. This concept originated in the 1990s, looking at POPs and also at methylmercury. And the investigators found that the delta N15 stable isotope value was a useful tool, and that these concentrations of POPs increased with D15N. Later, this was refined to calculate an integer-based trophic level for each individual organism that was being analyzed in the field study. TMFs are regarded as the most reliable tool for bioaccumulation and are increasingly used to quantify biomagnification. So, turning to an example of one approach, McIntosh et al. Examined a wide range of phthalate esters and PCBs in 18 species from a marine food web in an urban area of Vancouver, Canada. And they determined the delta 15N for each organism. And vertical axes shown here have lipid equivalent concentrations. The horizontal axis is the delta N15 for each organism. And also what we've added on top of that is we've calculated the trophic level approximately and put a scale on there. The trophic level is calculated showing that equation on the upper right, in which you assume that a sessile organism, such as a clam or plankton, if you have no other herbivore-type organisms, has a trophic level of 2, and that the change of N15 between trophic levels is 3.4. So on that basis, you can calculate a trophic level of each individual sample that's been analyzed. For the diethyl hexylphthalate and other phthalates, you can see that the concentrations actually declined across the food web, and this negative trend is due to biotransformation. And it's unlike that for PCBs. So the conclusion here is that the phthalate esters do not biomagnify in a marine food web. And of course, a prediction just based on the log KOW would imply that the BCF of the phthalates would be quite high, but of course it is not actually as well in lab tests. And I've put on here the PCB heptachlorobiphenyl 180, which is a highly bioaccumulative compound, and you can see, of course, that its concentrations are increasing across the same food web. And it's important that studies like this probably include a bioaccumulative chemical or some sort of internal check like this to compare with the performance of the studied chemical. There are uncertainties in applying the TMF, especially in, for example, harbors and other areas where there's wastewater inputs, because you can get a signal from that affects the D15N in primary producers. And also there's seasonal variation of D15N, which can confound the interpretation of the TMF data. So turning to a sort of wrap-up of the bioaccumulation area, the conclusions of the expert groups that focused on bioaccumulation was that the bioaccumulation criteria currently being used to identify POPs under the Stockholm Convention may need to be revised. In many cases, as illustrated for the phthalate esters that predicted BCF from the log KOW is not a reliable indicator of biomagnification. The most relevant criterion the working groups felt was the trophic magnification factor, because it averages the results of bioaccumulation or biomagnification over the entire food web. And in the absence of data on TMF, the biomagnification factor, either derived in the laboratory from dietary tests or based on field data, is a reliable indicator. Also, another aspect which you haven't really dwelt on here but is important is that both air and water-breathing organisms need to be considered, because studies have shown a slightly different suite of chemical accumulates in air breathers compared with animals taking up directly and eliminating over their gills. The BCF is not a good surrogate for BMF or TMF in terrestrial and aquatic food chains. And in fact, an analysis of draft risk profiles prepared for the Stockholm Convention found that of about the 20 substances on the current list, 5 were actually bioaccumulative, although BCF criteria were not met. But the BCF is appropriate for chemicals with log KOW less than 4. These do not normally biomagnify, and there's no evidence that these substances have BCFs greater than 5,000. So thus BCF or BAF for these more polar substances, which are accumulated mainly from water, is acceptable. And exceptions are the perfluorinated compounds such as PFOS and methylmercury, which are ionizable, but because of their unique structure and characteristics, they do biomagnify. And you can imagine as well that the BAF to BCF ratio is a potential indicator of biomagnification, but only in aquatic food webs, where, for example, a top predator fish would get its chemical mainly from the diet, whereas its prey may get it from water and diet. So I'll now just finish up by citing the 3 papers on which this presentation was based, and urge webinar attendees to look at these papers. They have much more detail. We've just basically touched the surface of many of their conclusions, and also to acknowledge the many contributors to those papers and to the working groups at the POPs PBT workshop. Now, moving on to ecotoxicity, we'll turn to the issue of toxicity data used to identify and classify PBTs and POPs. We'll begin with a listing of the criteria that are currently used and with some examples of the available data. And then we'll move on to a discussion of dose versus body tissue residues as better indicators of toxicity, and finally to recommendations for a tiered approach to assessment of ecotoxicity, which also applies to humans, although the focus here is on wildlife. Borrowing again from Gary's summary slide, this table presents the current criteria for assessment of toxicity. The criteria for the Stockholm POPs and UNECE protocols is rather general, but is focused on ultimately determining significant adverse effects as defined by expert judgment. Other agencies, in reviewing data for existing substances or new substances, are a bit more specific. But you'll see that the units are milligrams per liter, and it's interesting that most of the criteria are actually based on aquatic toxicity. This slide illustrates the type and quality of the toxicity data used in risk profiles for chemicals recently added to the Stockholm Convention, that is PFOS, pentachlorobenzene, hexabromobiphenyl, and chlordecone, or proposed to be added in the case of the short-chain chlorinated paraffins. These substances had a reasonable amount of aquatic and mammalian toxicity, indicated by the Ys as you read across, but they lacked avian toxicity, also lacked soil and sediment-dwelling toxicity, which is a major gap considering that most of these chemicals do end up in sediments and soils. Also limited data on carcinogenicity. Actual measurements of body burdens in key wildlife species and in humans was also limited for some of the chemicals, especially HBBB and the chlordecone. The risk profile reports on the POPs in the previous slide combine data from various endpoints of concern to conclude whether a substance meets the key POP toxicity classification of producing significant adverse effects on a global scale. But a closer look at the information cited in each profile showed they lack consistency in the type of endpoints considered and the amount and type of data included to substantiate the endpoint. So an objective for future risk profile reports would be to follow an established evaluation scheme based on a tiered approach to ensure that all the same endpoints are considered and the amount and type of data derived from these endpoints are uniform. We'll discuss this in a later slide. The assessment of data on toxicity involves evaluation of the quality and applicability of the literature data. For many chemicals, the database is small, and indirect methods of characterizing toxicity, such as QSARs or extrapolations with modes of action, are necessary. In the context of POPs and PBTs, which have high log KOWs in general, the definition of chronic is of relevance, as there is a concern that effects from such substances may be difficult to detect in short-term exposures in test conditions. Duration of chronic tests can be defined in relation to the half-life of a substance within the organism, while definitions of specified durations covering a large part of the lifespan of a species. And this is obviously more easily achieved with species that have shorter life cycles, such as invertebrates. And in fact, the 21-day Daphnia reproduction test and OECD 211 test is an example of a relevant test because it covers a significant part of the life cycle of the organism, includes mortality, growth, and reproduction. However, for an assessment of large, long-lived mammals, such as seals or polar bears, which are often cited in various POPs assessments in terms of exposure, extrapolation is necessary from data with smaller, short-lived mammals, such as mice and rat data, and obviously then leads to great uncertainties in the assessment. Ideally, the toxicity test must define both the effect response and the dose metric as precisely as possible. The best relationship is when the amount of the chemical at the site of action is known. The available toxicity data for chemicals with POPs characteristics may not be sufficient because of the potential for the chemical to bioaccumulate or biomagnify in the food web. In a standard toxicity test, as I mentioned earlier, the uptake from an environmental media such as water may be less than the uptake from the food chain, and so maximum target organ residues may not be reached in that particular toxicity test. So the potential adverse effects may be underestimated when the exposure is expressed as a function of the concentration in the environmental matrix. So ideally, concentrations in the target tissue or some other representative tissue, such as blood, should be used as an effect measure with a test duration of sufficient length to achieve steady-state concentrations and allow toxicodynamic evaluations using a modeling approach such as I showed earlier. Measurements in tissues of larger organisms such as liver are feasible, and you can see that being done in mammals and fish and birds and so on, and sometimes they can be compared with data from field monitoring programs. Concentrations in food or abiotic media, in other words, in the surrounding media like water, are useful, but less so than direct measures of the dose in the tissue. The next slide shows a tiered approach recommended by the working group on ecotoxicity. Tier 1 provides a simple scheme to screen out those substances that are highly unlikely to pose significant adverse effects. In this tier, you have two different sets of trigger values depending on the amount of data available. If you work from the top down, if you have less of data available, the uncertainty is larger, and you would therefore conclude that there's more toxicity data needed or more risks not be excluded, and you would head to the right-hand side, to the pink side. A more realistic risk assessment is with less generalization is possible when there are more data, in which case you could, if your thresholds such as those shown in the upper box are not exceeded, then you can come to the conclusion of a low significant adverse ecological effect. The group recommended those particular thresholds as reasonable ones to make that conclusion. Now, working from the bottom up, and this is mainly thinking in terms of chronic data, if chronic data are available for at least several representative species, then uncertainty for potential adverse effects is reduced, and smaller trigger values can be used to conclude whether there's an unacceptable risk or not. And in this case here as well, the working group has recommended various thresholds, such as 0.01 milligrams per liter of an NOEC as a general threshold for aquatic exposures, or in terms of 30 or 50 milligram per kilogram body weight in terms of mammalian and bird exposures, respectively. Now, if necessary, the assessment will move on to a Tier 2, and that's shown in the next slide. This provides a scheme for further evaluation. Again, it's split into two scenarios. One describes the procedure and triggers if the data are limited. The other provides triggers for substances with substantial and relevant databases. You note that we've now brought in predicted environmental concentrations, or PECs, or measured environmental concentrations, MECs, and also ratios of the no effect concentration to those predicted concentrations. And you can see potentially moving to the right if significant adverse effects cannot be excluded in the pink. But if there's sufficient data, then and NOECs divided by PECs are greater than 100, then this indicates a low risk and a conclusion of low risk of significant adverse ecological effects. Tier 3 is achieved, however, when the available data indicates the NOEC over the PEC is less than 10, or that there are many uncertainties. The conclusion of the working group here was that an expert review panel needed to take charge at this stage to evaluate the data. So to wind up the ecotox area, the characterization of significant adverse ecological effects is a challenging area because of the lack of appropriate toxicity and ecotoxicity data in many cases. Because POPs are persistent and bioaccumulative, the assessment of toxicity should be based on body or tissue residues causally linked to adverse responses because of the potential for these particular chemicals to accumulate or biomagnify in an organism's food web. But the definition and criteria for evaluating toxicity need to be clearly defined. And the use of an evaluative scheme based on a tiered approach is recommended to ensure that all the same endpoints are considered in each assessment and that the amount and type of data used for these endpoints is uniform. It's also a fast and cost-effective evaluation for non-critical compounds without losing protection goals on one side or being unnecessarily overly conservative on the other. The lack of specific data could be partly compensated by a weight of evidence approach, but the working group cautioned that extrapolation using that kind of approach may increase uncertainties. So the working group, again, is mentioned here. It's a paper by Keith Solomon et al. In IEAF, and also the members of the individual working group are acknowledged on this slide. And that ends my section on bioaccumulation, and hopefully there's time for questions.
Thank you, Derek. There was a lot of material in that segment, and we do have several good questions from our audience, so I'll get right into these. First one of these is for BAF. Does the requirement for dissolved phase concentration in water mean that the water samples have to be filtered in order to remove the particulates, or is it possible to simply collect samples to exclude suspended sediments?
Well, that's a good practical question, and I would say yes, that in general, the water concentrations do need to be filtered to really get a defined dissolved phase.
Okay, the second question, and really the questioner is asking for a short version. I'm sure there's a lot of detail that this could be pursued with, but really the question is why TMF is a better parameter than BMF.
Yeah, good question. I think that the quick answer to that is that because it averages magnification across the whole food web, so you don't have to be concerned about the selection of individual predator-to-prey relationships. You're actually averaging it. But, of course, you do need to collect the appropriate organisms over that food web in order to make the TMF work. So it involves more work, for example, than just collecting an individual predator and its prey.
Thank you, Derek. Let's go ahead and move along to the third segment of our presentation. today. And our final expert is Dr. Michael McLaughlin, who's a professor at Stockholm University in the area of environmental analytical chemistry. And among his areas of expertise is linking monitoring, field, and laboratory experimentation with modeling to better understand fate and bioaccumulation. So he's going to give us some perspective on bringing all this together. Michael?
Thanks very much, Bruce. Now we will then move on beyond the screening criteria to have a look at exposure assessment in the context of POP PBT risk profile. This is typically a higher tiered assessment step when evaluating POPs and PBTs. First, let us then define what we mean by exposure assessment. Here we have a figure illustrating the continuum of chemical risk assessment, and it starts then with sources of the chemicals into the environment, moves through fate and transport of chemical within and through the environment into different environmental matrices, resulting in the external exposure of organisms, which is in turn translated into an internal dose, a target organ dose, and eventually a biologically effective dose, which can lead to effects. Now, exposure assessment then takes into consideration then that part of this continuum, which goes then from sources, then through to one of several endpoints, depending on the tools which we are using for assessing it, either external exposure, such as concentrations in air, water, or foods, internal dose, such as a whole body concentration of a chemical, or target organ dose, which in some cases also. So in today's presentation of this area, following that brief introduction, I'd like to tell you a little bit about exposure pathways. Then we'll go on to look at how measurements can be used to assess exposure. The second major block will be exploring how models can be used to assess exposure. I'll close then with a short summary. So exposure assessment of POPs and PBTs generally focuses on humans or on top predators, as they typically have the highest exposures to these chemicals. Human exposure can occur by a number of pathways, including ingestion, dermal uptake, or inhalation. And the same exposures are generally also relevant for top predators. In some cases, it may be necessary to characterize each of these exposure pathways, but in general, dietary exposure is most important for exposure to PBTs, POPs. As we see in this picture, then, this dietary exposure can be very complex. There can be complex pathways then resulting in this exposure. Here we have a Great Lakes pelagic food web, and we can see that the different fish involved in this food web are themselves feeding on several different fish, and occasionally they also feed on themselves. It may be necessary then in our exposure assessment to take this complexity into consideration. Let us now move on to discuss how we can characterize exposure via measurements. One important factor to consider is what matrix to measure the chemicals in. Most POPs, PBTs, are lipophilic in nature, and hence it is important to measure in a matrix containing lipids. Three matrices that are commonly used for assessing exposure in humans are listed here. So adipose tissue has the advantage then that it is commonly the major reservoir of the chemical within the organs, making it good to analyze. But on the other hand, sampling adipose tissue in humans is a highly invasive technique which restricts access to samples. Breast milk has the advantage of better access, good detection limits. It gives us a direct measure of infant exposure, which can be something that interests us. But the quantification of the lipid content, which we need for our exposure assessment in many cases, can be quite cumbersome. That is much less a problem than when we are analyzing blood. and blood is also the most readily available of the matrices, but generally need more sensitive methods than analysis. Same considerations apply when selecting tissues to analyze in wildlife, but in addition, other factors must be considered when choosing the species. These factors can include then, of course, that accumulation can be expected in the tissues. The commercial or economic importance of the species may also be a factor in our choice. And then, if we are interested in assessing in particular biomagnification then through the food chain, then factors such as the lifespan of the organism, the documentation available on its feeding habits as well as its life history and behavior may be important. And certainly we also generally look for non-migratory organisms so that we can clearly associate then what we measure in the organisms with the habitat in which they live. In assessing exposure, then, we can work with different levels or different scales of effort. The most simple and the most common, then, is a survey, which is a sampling program of finite duration. A surveillance, then, is simply a repetition of standardized surveys to detect change, whereas a monitoring program, then, is a long-term series of standardized surveys to assess acceptable change. Here we have some examples then of monitoring and surveillance programs then for POPs and also for some other programs. I won't go into it in detail, but you can see that there are a wide range of both organizations dealing with this, the kinds of chemicals that are being studied, and the kinds of matrices as well that have been studied. And it is very important then to draw on the wealth of experience that has been gathered then in these programs then when designing new monitoring or surveillance programs. So let's move on now to talk about using existing data to quantify exposure. What should we be considering there? Well, one thing is then matrix suitability. Does the matrix actually demonstrate exposure? The type of data can be a consideration. For instance, then whether it is dry weight, wet weight, or lipid weight normalized. The representativeness of the data is very important. For instance, is the sampling site impacted by a local source, or is it truly remote? Temporal coverage of the data then can be an important issue as well. And QA, QC, so the available documentation then on the quality of the data is always imperative to look at. And finally, the interpretation of the data, how have the data then been pre-interpreted or filtered then can be very important. For instance, how have non-detects been treated then in developing statistics? If we then wish to use new measurements to quantify exposure, then the most important first step is to clearly define the objectives of your program. Different objectives could be, for instance, what are the levels in apex predators or humans? Or what are the trends then of a specific compound then over time? Or a more challenging and sophisticated question might be, does this compound biomagnify as well as bioconcentrate? Then, once you have decided upon that, you can decide on the scope of the data collection, and that is typically determined by the resources available to you. And then you can start asking questions like, for instance, is it possible to use existing extracts or sample banks? Or is it possible to use existing analytical methods, or do you have to invest a lot of resources in developing a new one? Once you've decided that, you can go on to the study design, determining what, where, and how often you're going to sample, establishing the protocols for your field methods, and developing an important developing a QA/QC brings us back to a very important topic, QA/QC considerations, which apply equally then to both using existing data and gathering new data. You want to have a validated analytical method, and you want to make sure that you have instrumental and method detection limits which have been well characterized and which are suitable for the purpose. Moving right along here, we also need a method then which has well quantified accuracy through, for instance, the use of reference samples, surrogate standards, spike samples. We want to furthermore then make sure that the issue of precision then has been taken into consideration in developing the method, that there is good evidence of precision and through replicate field and lab samples. And finally, that field and lab blanks have been taken into consideration and are well documented. For more information on this area then of exposure assessment then via measurements, I would like to direct you to the paper by Swackhammer et al. On the use of measurement data in evaluating exposure in this IEAM volume, and to acknowledge then the experts then who got together at the conference then and contributed their expertise and experience then to coming up with this document. We'll now move on then to the final lap then in our talk, and that is to assess, to explore how models can be used to assess exposure. Here we see then an example of how we can link up then models then. We start then with the fate of the chemical in the physical environment, which is illustrated then by the box at the left. We have emissions of the chemical into this environment, and the model then uses the physical chemical properties, such as partitioning coefficients or degradation rates, and properties of the environment, such as temperature and the organic carbon content of the soil, to predict the concentrations in the physical environment. These concentrations are then the starting point for the bioaccumulation model. It takes this together with the properties of the chemical and of the food webs to predict the concentrations in the organisms. In the end, we get the relationship between the chemical emissions to the environment and the concentrations in humans or in top predators. If we then want to also assess long-range transports, such as is required in assessing POPs, then we can do this then by emitting the chemical into a physical fate model and then calculating the transfer of, or the fraction of chemical transferred from that region of emission then to a more remote region where we repeat the process that I outlined in the previous slide. I'd like to now go through then strategies that can be used for assessing exposure in developing a risk profile. The first is ground truthing, and this is the comparison of model predictions with monitoring data. What it tells us is, are the model and monitoring data reasonable, representative, and consistent? And this can either lend credibility to, or it can question monitoring data, whether they are good or bad, the physical chemical properties that we use as input to the model, or emissions estimates that have also been used then within the model. In general, then, ground truthing can be used then both to build confidence in models and to discover areas of ignorance. A second strategy for using exposure models is confronting uncertainty. This allows us then to bound the estimates of exposure that we have. A point estimate is of little value as a rule. We want to know then what range could the exposure actually lie within. This information can be very useful as well in directing efforts to improve exposure estimates. So, we have poor information on chemical emissions, we can use this technique then to compare the inherent tendencies of chemicals to reach the biological endpoint that we are interested in. Fourth strategy is then prediction. We can predict concentrations and endpoints then given known emissions. And this can be very helpful, for instance, in designing sampling programs and defining the LOQ, for instance, that we need for analytical methods. Forecasting is another very obvious use then of exposure models. We can use models then to predict future time trends based on existing emissions information. And in an extension of that, we can also use them in a scenario testing manner then to test how different risk management options will influence exposure in the future. What I would like to do now is to use a case study to illustrate some of these strategies, which have certainly remained quite abstract to many of you. I will emphasize the word illustrate, as it is not a definitive exposure assessment. We did this assessment using the model, which is shown here, then the radar model, which is a steady-state exposure assessment model developed by John Arnott. What we first did, and what I'm showing you here, is a ground truthing exercise then for the chemical 2,2'4'4'5' pentabromo diphenyl ether, so a PBDE congener. And the data that we used were based largely on information in the POPs Review Committee risk profile for this chemical. And we had a regional environment of 100,000 kilometers squared and a population of 8 million. Emissions, again, derived then from the same data sources, and we used monitoring data largely from the UK for the years 2000 to 2004. And we predicted then the concentrations in a whole range of matrices, and you see some of them in this figure. And we compared then the predicted values, which are shown as an X, a point estimate, with the monitoring data, which are shown with a circle and error bars. And you can see then that in many cases we have very good agreement then between the model predictions and the monitoring data. This gives us confidence in the models, in the monitoring data, and in our general understanding of the exposure. Here is another series of matrices that were studied. Again, the concentrations then being plotted along the x-axis for different vegetables, foodstuffs in this case. And here we see an example then where there is a discrepancy of about an order and 1.5 orders of magnitude then between model predictions and observations, suggesting that maybe something is wrong and helping us then to take a critical look then at the information that was used. Confronting uncertainty was also done then using the same chemical. And here we did a model sensitivity and uncertainty analysis using a confidence factor method, and I will not go into the details here. And we assessed then the uncertainty arising from the physical chemical properties that were used in the model. And here you can see then the results. We have on the x-axis at the bottom then the sensitivity or the contribution to variance expressed as a fraction. And we have then on the vertical axis then the different physical chemical properties that were studied. The blue bars show the sensitivity, and we can see that the sensitivity is greatest then for the biological transformation half-life of the chemical in mammals and birds. We can then take the information then on the uncertainty of the different input properties to calculate then the overall uncertainty that they contribute to the total uncertainty for the endpoint. We compared then known POPs and known non-POPs as well as
candidate pops using a benchmarking exercise to again illustrate this. We had the same emission of each chemical, and we compared the human body burden. And what you see here then is the concentrations in red, or the human body burdens on a logarithmic scale for 4 different chemicals. And they range then between 10 to the minus 5 and 10 to the minus 2. And you can see the non-pops, shown in green, have much lower concentrations. And you can see the candidate pops here in blue all have concentrations which are very similar to the concentrations of the known pops. And this gives us then some indication that the persistence and bioaccumulation properties of these chemicals of the candidate pops are comparable then with the known pops. So in summary, a few take-home messages for you. The integration of monitoring and modeling is important to the exposure assessment of POPs and PBTs. The definition of the objectives and careful planning is a key to obtaining useful monitoring data. A high standard of QA/QC from sampling through to quantification is also essential then for obtaining good data then for exposure assessment. And finally, benchmarking is finding increasing use in exposure assessment. I would like to close then by giving you a brief run-through of the overall framework for POPs and PBT evaluation, which was a result of this Pelston workshop as well. The first question that we start with at the top here is the purpose of our PBT or POP assessment a rapid review of substances or a detailed assessment of one or a few chemicals of concern? In the latter case, we go straight down to the assessment phase, whereas in the former case, we go through a priority setting phase, which employs rapid, inexpensive, and conservative prioritization tools for persistent bioaccumulation and toxicity. And in the case of POPs, then LRT, and can also use any existing data. If that indicates then that we have a potential PBT or POP, then we go on to the assessment phase, and that involves a more accurate and precise assessment of PBT and LRT, using both empirical data and substance-specific modeling, and using a weight of evidence approach. If we still, based on that assessment, come to the conclusion that we have a potential PBT or POP, then we move on to further assessment and or regulatory action. So now that concludes then this part of our presentation, and I would like to direct you then to the Cowan and Ellsbury paper then for more information on modeling exposure to persistent chemicals. And I would also like to acknowledge the experts then that contributed then to this work and preparing this paper. And with that, I would like to hand this back to you then, Bruce, and apologize once again for the interruptions.
Thank you, Michael. Appreciate everybody's patience with our technological challenges here. I think at this point what I'd like to do perhaps is answer or ask one quick question that's actually been posed by several of our audience members regarding some points that Gary had made in his portion of the presentation. And that is that mention was made of the fact that the detection of a chemical in a remote area is not in and of itself sufficient to prove its persistence or long-range transport properties. Could you provide a little bit more of an explanation of why that is in fact the case?
I sure can, Bruce. And this is taken directly from Martin Scheringer's paper. I think what this reflects is in part the uncertainty, because Martin and his colleagues note that it's important that a more critical appraisal of a chemical's occurrence is made. Detection reflects the sensitivity of the analytical methods, the rigor of the sampling, and the possibility of local sources and contamination. And presence is obviously a function of uses and emissions. So I think what their point is that it's not evidence per se that a chemical is persistent or subject to long-range transport, that if you find it in a remote region, you need to do a lot of critical evaluation of that data to be sure that you believe it, and then secondly, is it consistent with the behavior of the chemical that you might predict?
Thank you, Gary. And I think with that, I will summarize here 2 points for our attendees. First of all, thank you very much for sticking through what is a lot of material presented today, and we want to remind all of you, or ask that all of you fill out the survey, and in particular pay attention to the questions relating to what you would like to see either in more detailed webinars on this particular topical area, or perhaps some other topical areas that you would like to see CTech present webinars on. And again, this survey will be available to multiple respondents. So if you have multiple folks viewing the webinar at your location, several of them will be able to provide feedback to us. Lastly, I know a number of you asked about the availability of the presentation. You will be receiving an email shortly with a link showing where the archived copy of the presentation as well as the audio is available and can be downloaded. So again, we appreciate you all staying tuned in for this, and the survey will be up and available for you to respond to, even though we are going to sign off shortly. Thank you all very much.
Thank you, everyone, for attending today. That does conclude today's conference. You can please complete the survey as Bruce indicated, and you can hang up at any time. Thank you, and have a great day.